Lecture 4 is the beginning of our series on spectroscopy. This is part 1, mass spectrometry. Part 2 is going to be NMR, and we're going to do that in 2 lectures. And then part 3 is going to be infrared spectroscopy and X-ray crystallography. So what is spectroscopy? Spectroscopy is part of a larger task in organic chemistry, which involves identification of organic structures. When we talk about identification of organic structures, what I mean is when you make something in the lab, how do we find out what we actually made? How do we find out if it's the right structure, if it's the right enantiomer, if it's chiral, if it's not chiral? How do we tell if it's pure or if there are impurities? If there are impurities, what are they? And based on what they might be, we can figure out how we might want to separate them. So, when a compound with interesting properties is isolated from a natural source, let's say when we figured out that penicillin is a useful antibiotic that's produced in mold on bread, we want to figure out what the structure is of the molecule so that we can make it in a lab. Eventually, we're going to want to stop having to harvest mold from bread if we want to make penicillin. So we have to make it in a lab. And before we can make it in a lab, we have to know what the structure is. Also, like I mentioned, when we run a reaction, we want to figure out whether the product has the structure that we want. And we can figure out the structure of any unwanted byproducts so that we can figure out how to separate them or maybe alter reaction conditions to favor the desired product. So there are many ways of identifying a compound. You've probably done many of these in lab already. Some chemical methods, which I'm going to show you in a minute, differ from spectroscopic methods. Chemical methods might involve determining the molecular formula by doing elemental analysis. If you took general chemistry, we talked about elemental analysis and how it's done and what information you can find out. You can also look for physical properties by doing, say, a melting point or boiling point experiment. You can measure the solubility of a compound, how soluble it is in water or octanol or some other solvent. You can measure the heat of vaporization. You can do reactions on it, like ozonolysis. Look at the byproducts of ozonolysis, or do a titration, or do a reaction that gives you Markovnikov or anti-Markovnikov addition, and look at the product that you get, and then from the product you can determine what your starting material must have been, etc. These are all methods that you could use to determine what the structure of a molecule is, but there are some drawbacks of these methods. First of all, in all these cases, the test sample must be pure. If you send in a compound for elemental analysis that's got impurities in it, your elemental analysis is going to be wrong. If there's maybe sulfur or some kinds of metals or other sources of carbon in there, your ratios are going to come back wrong. If your melting point or boiling point experiments have impurities in your compound, your melting points and boiling points are going to be too high or going to be too low. Same with your solubilities and your heat of vaporization. Another part of this is that a large amount of material is required for these things. These are destructive methods. Usually, like in ozonolysis, you take your molecule and you ozonolize it, and you look at the products are, and then based on the products, you kind of put Humpty back together again and figure out what your starting materials must have been. So in that case, you're destroying what your molecule was in the first place. So if it was expensive or difficult to come by in some way, or you spent 4 years in a lab making it, you don't really want to destroy it just to figure out if you had what you think you had. And because of that, large amounts of material are required. You can't do these reactions on micrograms because the amount of product that you get is going to be so low that it's going to be indetectable. In a lot of these cases, substances must have been characterized previously, meaning that if you're going to do a melting point experiment and figure out that your melting point of your molecule is 112 degrees Celsius, you have to compare that to some reference. You go into a reference book and say, okay, what other molecules have melting points of 112 degrees? And which of those make sense as possible candidates for my structure? Same thing with boiling points and melting points. Those physical properties don't tell you anything about your molecule unless there has been other methods that have been verified that have those values associated with a certain structure. And because of that, conclusions are often vague at best. So chemical methods, kind of messy, kind of uncertain, kind of destructive, kind of expensive, not ideal in a lot of cases. So, how do those differ from spectroscopic methods? Well, what are spectroscopic methods? Spectroscopic methods basically exploit the absorption or emission of electrons or some kind of electromagnetic radiation, for example, light or magnetic fields, by different structural elements. For example, if we're looking at, say, how a molecule absorbs infrared light, it turns out that different structural elements like ketones or aldehydes or carboxylic acids or alkenes or alkynes absorb different frequencies of light. So if you look at your molecule and say, what frequencies are these molecules absorbing? You can go back and say, okay, therefore, I must have these structural features present. So that's basically what spectroscopic methods do. You look at how these molecules absorb or emit electrons or radiation, and from that, you can infer what your structure is. So, like I mentioned, we're going to start with mass spectrometry. Mass spectrometry basically breaks a molecule into fragments, and then it weighs the fragments and sorts them. Different functional groups on a structure will tend to induce different predictable fragmentation patterns. So, based on how your molecule falls apart, you can figure out what caused it to fall apart that way. One drawback, of course, is that it's destructive, but fortunately, less than 1 milligram of material is typically required. You can do a mass spectrometry experiment with very, very, very little starting material. So even though it's destructive, you really don't need much of your substance to start. You can first separate impurities by a method called GCMS. We're going to talk about in our lecture. Later on in lectures 5 and 6, kind of the second part of our spectroscopy series, we're going to talk about nuclear magnetic resonance, or NMR, where we're going to look at how different chemical environments behave differently under different magnetic fields. This will give us evidence for the structures of alkyl groups and also evidence of functional groups. NMR is non-destructive, which is very nice, and significantly less than 1 milligram is required. One drawback in NMR is that impurities can make results more obscure, but many times you can actually identify what your impurities are. Even though they're not separated, you can at least figure out what they are. In the third part, we're going to talk about infrared spectroscopy, which induces vibrations in bonds through the absorption of infrared light. And from the absorption and emission of infrared light, we can figure out what functional groups are present. So all these three techniques are complementary, meaning that usually one is not sufficient to fully elucidate the structure of your molecule. So we're going to be using them in conjunction with one another. They are most powerful when they are used together in combination. In many cases, an unknown compound cannot be completely identified from one spectrum without additional information. So you can't figure it out just from mass spec, or you can't figure it out from just IR or just NMR, but you can figure it out when using two or more of these types in conjunction with fairly high confidence. So we're going to begin with mass spectrometry. So again, what we're going to be doing is we're going to be breaking molecules into fragments. We're going to be weighing and sorting the fragments. We're going to use our understanding of functional groups to figure out how functional groups will induce different predictable fragmentation patterns. And we're going to talk about other methods for separating impurities, such as GCMS. So what does the mass spectrometer look like? This is a schematic of a mass spectrometer. In a mass spectrometry experiment, your sample is injected into the machine and it is bombarded by a beam of electrons. Those electrons cause the molecule to fragment into ions, which are then accelerated through what's called the flight tube by a magnetic field. Since ions are charged, they will interact with the magnetic field. The flight tube is curved around a magnet, and that's very important because at any given magnetic field strength, only ions of the appropriate mass will pass through the flight tube. Ions that are too light will bend too much and they won't make it through. Ions that are too heavy will bend not enough and they won't make it through. But ions that are only the specific mass that we want will make it around that curve and eventually will hit a detector which records when ions impact it. So imagine as we start our experiment, we'll start with a low magnetic field. And as our molecule is ionized, the lightest ions will be pulled through the flight tube and hit the detector. Then the magnetic field will increase and heavier ions will make it through and hit the detector. And eventually the magnetic field will be so strong that the heaviest of the ions will make it through the flight tube and hit the detector. So as the magnetic field strength is ramped up, the ions that hit the detector increase in molecular weight, and the machine will record the molecular weights of the ions. Not exactly that it's measuring the weight of the ions, but based on the strength of the magnetic field, the machine knows the molecular weight of the ions that should be passing through the flight tube and hitting the detector at that time. From the outside, this is what a mass spectrometer looks like. This is a very large model, but you can basically see here's the probe where the sample is injected. Their beam of electrons will pass through the sample and will accelerate the particle fragments through the flight tube around the magnet, which is right here, and eventually will hit a detector that will then be recorded by a computer. We have smaller tabletop models now that look something like this, where you can now, the mass spectrometer is so small that it can be coupled with what's called a gas chromatograph, which is basically an oven that helps us separate our molecules based on boiling point before they pass through the mass spectrometer. So as you can see, we can use mass spectrometry to elucidate the structure of our unknown compound based on fragmentation patterns that we can then look at the fragmentation patterns that we see and infer the structure that we had. So, like we said, the mass spectrometer ionizes or fragments a molecule in a vacuum using a beam of electrons. It sorts the ions or fragments according to their masses by using a magnetic field. It records the relative abundance of each ion of each mass, and it gives us what we call a mass spectrum. That is basically a plot of, on the x-axis, what we call m/z, which is a mass to charge ratio. Now, most charges in organic molecules are +1. So your z is pretty much always going to be 1, which means that your mass to charge ratio is basically just your mass. So on your x-axis is your mass, and on the y-axis is the abundance of those particular fragments. So on this mass spectrum, you see that whatever a molecule was broke into different fragments that had these different masses. There was a fragment that was 55 molecular weight units, 159, there was some at 69, one at 74, 87, 101, 115, 127, 143, and 158. So lots of different fragmentation patterns. Now, ideally, what we could do is we could use some detective work to figure out what these molecular weights refer to in terms of organic structures and figure out then what our original molecule must have been. There are a couple important features to a mass spectrum. The first is the parent peak. The parent peak is the largest molecular weight peak, which is typically the molecule that has basically ionized but hasn't fragmented. So the parent peak will tell you what your molecular weight is. That's often abbreviated as M+. Basically what happens here is an electron gets knocked out, so you have an ion, but the molecule makes it through the flight tube before the molecule actually fragments. The other feature that we often look for is the base peak. The base peak is not the smallest peak, but it is in fact the largest abundance peak. So it has nothing to do with the molecular weight, like the parent peak has the highest molecular weight, the base peak has the highest abundance. And often what we'll do is we will use this to figure out that means that that's the most common or favorable fragmentation site. Maybe that is a particularly weak bond that causes our molecule to fragment into a piece that weighs 74. Maybe the fragment, the cation, for example, is a very stable cation. Maybe it's an allylic cation or a benzylic cation. That will increase the likelihood that that fragment forms when the molecule breaks. So we're going to be doing a lot of detective work to figure out what our molecule looks like just based on this data. Now, like I referenced before, mass spectrometry is also coupled with a gas chromatograph. We call this GCMS, or gas chromatography mass spectrometry. A gas chromatograph is basically a very long tube, or what we call a column, that is coiled inside of an oven. Now, what we do is we inject our molecule, our sample, into the GC, and it is pulled through the column. And it is, of course, since it's an oven, it's basically turned into a gas. And the molecules will interact with the surface of the inside of the column to different degrees based on their different properties. So, for example, if we have a neutral column where there's no specific type of interaction between the molecules in the column, then they will basically be sorted by molecular weight. So if we've got a mixture of 5 different compounds in our sample, the heaviest ones will come through last and the lightest ones will come through first. Once they get through the gas chromatograph based on their molecular weight, then they will pass through the mass spectrometer, which will fragment them and sort their fragments by molecular weight. So this means that we do not need a pure sample. We can have all kinds of impurities in our sample, and the GC will sort them before they pass through the mass spectrometer. The GC is also pretty cool because you can use different types of columns. For example, you can use a chiral column, which will interact with only the S enantiomers instead of the R enantiomers. And that means that the S enantiomers will move through the column slower because they're interacting with the surface of the column, and the R enantiomers will not interact and they'll move through the column very quickly. That means that your R enantiomers will get to your mass spectrometer first, and later on your S will come through and hit the mass spectrometer second. So all kinds of cool ways to sort your mixture through the GC before they actually go into the mass spectrometer to generate your spectrum. So what this looks like, this is a GC, and this is basically a time scale. This is 5 minutes, 6 minutes, 7 minutes, 8 minutes, 9 minutes, 10 minutes, 11 minutes. So you see that early on in our experiment, we got these peaks. Here's a peak there, here's a peak there, there's a peak there. This is basically the time at which different substances in our mixture come through the GC. And what you normally can do is, if the GC is coupled with a mass spec, is you can click on each peak, and each peak will then have a mass spectrum associated with it. So let's talk a little bit about this fragmentation that I keep referring to. I mentioned that your sample in the mass spec is fragmented by bombarding it with a beam of electrons. So the way this happens is that when an electron strikes a neutral molecule, it will ionize the molecule by knocking out an additional electron. So here's our electron E minus, here's our molecule M. The electron will collide with the molecule and knock out another electron. These electrons will basically pair up and eject from the molecule. And what will be left with is called a radical cation. This is now a radical because we have an unpaired electron, and it's a cation because we have lost an electron. So it loses an electron, has a positive charge and an unpaired electron. We call that a radical cation. What happens then, that means that we have a bond somewhere that isn't really a bond anymore. That bond lost an electron. And what happens is, wherever that electron was ejected from fragmentation will happen at that site. Now, here's an example with ethane. Here's ethane. We're going to hit it with an electron. It's going to knock an electron out from one of these bonds somewhere. But notice that there are two sites that we could lose an electron from. We can lose an electron from one of the carbon-hydrogen bonds, or we can lose an electron from the carbon-carbon bond. Now, first what's going to happen is the electron is going to knock out one of the electrons somewhere. That's going to get us the radical cation that will have a mass of 30. The charge is 1, the Z is 1, and the mass is 30. That's the mass of ethane, is 30. So we will have a peak, the parent peak, at 30. But since here they show us knocking the electron out of the carbon-hydrogen bond, that will eventually fragment and we'll end up with a mass of 29 and an H. If instead the electron gets knocked out from the carbon-carbon bond, then the carbon-carbon bond will fragment, and what we'll be left with is a mass of 15. Now I want to show you something. Notice that in our parent here, our molecular ion, the site of fragmentation has one electron, and so when that breaks, the electron's going to go onto one side or the other. So if the electron goes onto the hydrogen, we'll get the hydrogen radical like they show here, and the carbon cation. If the electron goes onto the carbon, we would get the carbon radical and the hydrogen cation. Same thing here. When this cleaves, if the electron goes onto the fragment on the right, we'll have a methyl radical and then the methyl cation on the left. Or if the electron goes onto the left, we'll have the radical on the left and the cation on the right. So you can have various other combinations of radicals or cations. The point is that when it fragments, one side gets the radical, the other side gets the cation. But since only the cations are charged, they are the only ones that will interact with the magnet, and they are the only ones that will move through the flight tube and hit the detector. Essentially, the green fragments here, which are the radicals are invisible to mass spectrometry. We do not see the radical. So often it is the case that a bond will cleave either way, so that one side gets the radical and the other side gets the cation, or vice versa. But sometimes, depending on some certain structural features, it might be completely predictable that one side will always get the cation and the other side will always get the radical. For example, if the cation is next to something that stabilizes it by resonance, for example, then that side of the fragment will always get the cation because that's the more stable place to put the positive charge. So let's look at a more complicated example here. Let's look at 2,4-dimethylpentane and think about all the ways that this molecule might fragment. So the first thing that's going to happen is the electron's going to come in and it's going to bump an electron out of our structure. Now, we have primary, secondary, and tertiary sites on 2,4-dimethylpentane. So the most likely place to make a radical or a cation would be to knock an electron out of one of the tertiary carbon-hydrogen bonds. So that's why I'm showing the tertiary carbon-hydrogen bond losing an electron here. That gets us a radical cation. Our mass is the molecular weight, which is 100. We've only lost an electron, of course, so that doesn't affect the weight at all. We haven't lost any atoms yet. So the mass of the molecular ion is the molecular weight. And 2,4-dimethylpentane has a molecular weight of 100. So we should expect to see a peak at 100. Now, if we fragment that methyl, let's say we break that methyl off, we're going to get a CH3 plus and then the radical on the rest of the fragment. Or we're going to get a CH3 radical and the positive charge on the rest of the fragment. Both of those ways might happen. Now, obviously, it's better to have a secondary carbocation than a primary carbocation, but it's also better to have a secondary radical than a primary radical or a methyl radical. So both of these cations are probably going to form at some point. The methyl weighs 15. That's 12 for a carbon plus 3 hydrogens, which weigh 1. And this guy weighs 85. If you count up 1, 2, 3, 4, 5, 6 carbons plus all the hydrogens, this would be 85. So we'd expect to see a 15 and an 85 from this fragmentation site. We could also fragment here, which would give us a fragment of 43 from this piece on the left, the isopropyl fragment, and a piece of 57, this isobutyl fragment. We could also fragment off just a hydrogen, either at a primary site or, of course, at the tertiary site, like I showed, which we originally knocked an electron out of from the parent, in which case we would only lose one molecular weight unit. That would be 99 and 1. So these are the fragments that we should expect to see in 2,4-dimethylpentane. Let's take a look and see what we actually have. Here's the spectrum of 2,4-dimethylpentane. Here's 100. Again, the highest molecular weight fragment is the molecular ion. And in this case, it's 100. That's what we expected. Here's 85. Remember what 85 was? 85 was 100 minus 15, which is minus a methyl group. So 85 was what we got when we broke a methyl group off of our parent. So we've got 100, we've got 85. Here's our 57 and our 43. Remember that 57 and 43 were formed by the same fragmentation pattern right here, 43 and 57. We also got a 41, which I'll talk about in a minute. And we've got a bunch of these other things here. All these other minor fragments, these low abundance fragments, are all kind of clustered around our major peaks. So let's talk about why are peaks clustered. Usually it's because there are lots and lots and lots of ways that a molecule could fragment. You could get multiple fragmentations, which means you're going to have multiple cations, which means your MZ is not really going to be the molecular weight. It's going to be the molecular weight divided by 2. Sometimes you will see peaks that are 2 molecular weight units lower than what you would expect, and sometimes only 1 molecular weight unit than what you would expect. For example, we expected a 43, but a 41 is actually our base peak. That's our highest abundant peak. So we didn't expect a 41 based on our fragmentation pattern. We did expect a 43. So 41 and sometimes 42 could form from basically fragmentation followed by elimination, which means you end up forming alkenes in the mass spectrometer. You lose 2 hydrogens. Now, think about 43, which is our isopropyl group. If we lose 2 hydrogens from our 43, we'll get a 41, which is an allyl group. An allyl is very stable. The carbocation is resonance stabilized in the allyl cation. So often you will see, like I said, fragments that are 2 or sometimes just 1 molecular weight unit lower than what you'd expect. That simply means that the 41 came from the 43. That doesn't necessarily mean that there was a 41 fragment on our molecule. It just means that it came from a 43. Sometimes it might be the case that the 41 is actually on our molecule, that there wasn't a 43, but there is a 41. So be careful, but just sometimes just be aware of that you'll see fragments that are too smaller than what you'd expect. Also, be aware of isotopes. Remember that isotopes exist. Most carbon in the world is carbon-12, but about 1% of carbon is carbon-13. So that means that one time out of 100, your fragment might end up with a carbon-13 in it instead of a carbon-12, which means that your molecular weight will be 1 higher than it should be. For example, if any of our molecular ions have a carbon-13 in them, they won't be 100, they'll be 101. So maybe that's going to be very, very, very low abundance, so small that you can't even see it. But sometimes that might mean higher. That might mean that if you have a very high abundance peak, like 41, at say 100 abundance, you might have a 42 at about 1%. Now, obviously, it's higher here for other reasons, but be careful of that. Carbon can be carbon 12 or carbon 13. Hydrogen can be hydrogen 1 or deuterium hydrogen 2. Nitrogen can be 14 or 15. Sulfur can be 32 or 33. In fact, it can also be 34, which occurs at 4% abundance. Chlorine and bromine are even more exaggerated. Chlorine 37 occurs 24, nearly 25% of the time, which means that you have 75% of your chlorines are 35, 25% of your chlorines are 37. That's a 3-to-1 ratio. Bromines are 79 and 81 at about 50% abundance, meaning that half of your bromines are 79, but half of your bromines are 81. So if your fragments have a bromine on it, some of them are going to be a certain molecular weight, and about 50% of them are going to be 2 molecular weight units higher. So common isotopes can affect your molecular weights of your fragments, but we can also use them to identify their presence, of course. We can look for parent peaks or otherwise paired peaks that have a molecular weight 2 higher at equal abundance. So our M plus 2 is as large as our M plus. That means that we've got a bromine. I'll show you an example in a minute. For chlorine, since it's 75 to 25, we're going to see an M plus 2 about a third as large as the M plus, meaning that about a third of the time we're going to get a chlorine 37, and 75% of the time we're going to get a chlorine 35. Iodine, you're going to have a piece at 127. Iodine weighs 127, and iodine is a very common fragmentation site. If you've got an iodine on your molecule, it will fragment at the iodine, and you'll be missing a large molecular weight from your parent. That missing mass will be 127. Nitrogen, because of the fact that it makes 3 bonds instead of 4 like carbon does, means that you'll have an odd molecular weight and even fragments. So your parent peak will have an odd molecular weight and all your fragments will be even. That's different from if you don't have a nitrogen. If you don't have a nitrogen, your parent peak will be even and your fragments will be odd. So nitrogen is very easy to spot. And sulfur, that 4% abundance of sulfur 34 means that you will often see M plus 2 about 4% higher than M plus. So here's an example of a molecule with sulfur. Our parent is 76. That is the molecular weight of this based on the most abundant isotope of sulfur, which is 32. But 4% of sulfur is sulfur 34. And so you'll see these other peaks 2 units higher that are about 4% of the parent. So seeing that pattern suggests that we've got a sulfur. Let's look at some other isotopic signatures. Here's chlorine. Here's a molecule, isopropyl chloride or 2-chloropropane. The parent is 78 if it's got a 35 chlorine. But 1/3 of the time, 75 to 25, you'll have chlorine 37, which means that you'll see a peak 2 molecular weight units higher. That's about a third of the abundance. That pattern there suggests that there's a chlorine there. So let's look at what other things we have here. Our parent is 78. What is 63 compared to 78? 63 is 78 minus 15, and a methyl group is 15. So 63 is what we get from our parent if we lose a methyl group. But notice that what's left has the chlorine on it. So sometimes we'll lose a methyl group from our 78 and we'll get a 63. But other times we'll lose a methyl group from our 80 and we'll get a 65. So you see that any of the fragments that also have the chlorine on it will have that M plus 2 pattern. We've got a 78 and an 80. we've got a 63 and a 65. Why doesn't 43 have it? Because 43 is the propyl group. 43 is what you get if you take 78 and knock off the chlorine. So that's just the 3 carbons. So that does not get the isotopic effect since there's no M+2 on our propyl group. You might have a carbon 13 somewhere, which means that 1% of the time this might be a 44, but for the most part, it's just 43. Here's bromine. Like we said, 50% of the bromines in the universe are 79. 50% of the bromines in the universe are 81. So you're going to see 2 peaks of equal abundance separated by 2. This is 1 bromopropane. That weighs 122 if our bromine is 79. It weighs 124 if our bromine weighs 81. If we cleave off the bromine, we're going to have this propyl group again, this 43. So that means that we won't see that isotopic effect for the 43. But that is the main fragmentation pattern. We're either not going to fragment the molecule at all, and we're just going to have the parent ion go through the detector, which will have the bromine on it at both molecular weights, or we're going to cleave off the bromine and leave us with the propyl fragment of 43. So what do we see here? Let's test this out. Here we see this M+2, these peaks separated by 2 molecular weight units, and they're about 50-50 abundance. So that is the sign that we've got a bromine. Here we've got a large gap between our fragments, and we've got a 127. Notice that 29 plus 127 weighs 156. So 156 is our parent. If we break an ion off of our parent, whatever it is, we're going to have a 127 from the iodine, and then we're going to have 29 left over. 29 is actually an ethyl fragment. You can figure that out. So this is probably ethyl iodide. Ethyl iodide weighs 156. If you break off the iodine, you'll have a 27 from the I and the ethyl, which is 29. Here's 90 and 92. That looks like that's about 1/3 abundance. So I guess that's a chlorine there. We've got a chlorine on this molecule. And here we've got an odd parent with an even fragment pattern. We've got 100s and 86s. That is the sign of a nitrogen on our molecule. One of the most important things to learn in mass spec are the molecular weights of common alkyl fragments, common fragments of alkanes. This here is the mass spectrum of hexane, just N-hexane, 6 carbons in a row, C6H14. If you think about all the fragmentation sites of hexane, imagine cleaving off just a methyl group and leaving the rest. That would give you 71 from the 5 carbons left over, and then the methyl on the other side. Hexane weighs 86. So there's our molecular weight. Our parent is 86. If we cleave off a methyl, we lose 15. So that gets us 71, M minus 15. If we cleave off an ethyl, 2 carbons, we lose 29. And so we get 57. So 57 is our parent minus 29. If we cleave off 3, that's 2 propyl fragments, which are 43. So we're going to have a 43 and another 43. So 15 is methyl, 29 is ethyl, 43 is propyl, 57 is butyl, and 71 is pentyl. Those can be branched, so they can be a sec-butyl or a tert-butyl or an isobutyl or a regular butyl. 43 could be a propyl or an isopropyl, and pentyl could be any of the different isomers of a C5H11, basically. So here's the pattern for hexane. You see all the expected fragments there as far as molecular weight goes. What's interesting about this pattern is the abundance. Notice that it's very uncommon to lose just a methyl. It's more common to lose the ethyl. In fact, it's the most common that we can lose the ethyl. It's less common to lose the propyl. And you see that every time we lose an ethyl, we also will find the ethyl fragment. We can cleave it to make the cation on the 57, or we can cleave it to make the cation on the 29. The fact that the 57 and the 29 are made at the same time, notice that in order to make 57, we have to cleave off 2. The fact that you see more of the 57 and less of the 29 means that usually the cation goes onto the 57 and the radical goes onto the 29. But sometimes the cation goes onto the 29 and the radical goes on the 57. 43, it's going to be equal both ways because it's the same. It's symmetrical molecule. If you cleave at 43, you get half of one and half of the other. So it doesn't matter where the radical or the cation goes because it's the same either way. This is kind of what I'm referring to. If we cleave at the methyl group, we cleave off the methyl, we're going to lose 15 from our parent. We're going to lose 15 from our 86. We're going to 71 and a 15. But we could cleave the 71 to make the cation and the radical get the 15, or we can cleave to make the methyl the cation and the 71 the radical. But notice that that doesn't happen. We don't see a 15 anywhere in here. 15 is not there. So you're never going to make the methyl cation with the pentyl radical. That fragmentation pattern does not happen. The reason, of course, is because that gets you a methyl cation as opposed to a primary cation. It's more stable to cleave the molecule in such a way that you get the more substituted cation and the less substituted radical. So fragmentation will favor inductively stabilized or resonance stabilized fragments. By inductively stabilized, I just mean stabilized based on hyperconjugation by having the more substituted groups. Now, here's 2-methylpentane. It's not hexane anymore. It's the same molecular weight because 2-methylpentane is an isomer of hexane, but we've got a branch on here. We got a 5-carbon chain with a methyl branch. And you can see that we get basically the same fragments. We have our parent at 86. We lose a methyl to make 71. We lose an ethyl to make 57. We lose a propyl to make 43. But these abundances are noticeably different. Compare the abundance of 2-methylpentane's fragments to the abundance of hexane's fragments. With hexane, 57 was the base peak. With 2-methylpentane, 43 is the base peak, and 57 is quite rare. So think about why that is. Also notice that losing a methyl group is quite common for 2-methylpentane. 71 is quite abundant for 2-methylpentane, but 71 was not very abundant at all for hexane. And again, the reason for that has to do with how stable the cations are. If we lose this methyl group or one of the methyl groups here from our secondary carbon, actually this is a tertiary carbon, we will get a secondary carbocation. We lose a methyl from our tertiary, we'll have a secondary cation left over. So that's really good to get a secondary cation as opposed to a primary, which we would get by cleaving at many of these other sites. So losing a methyl is fairly common because it gets us a inductively stabilized cation. Also, 43 is very common. If we cleave right here, this squiggly line right there, we get an N-propyl fragment and an isopropyl fragment, and those both weigh 43. And again, isopropyl is very common. The blue fragmentation site gets us this pattern up here with a secondary carbocation, and the black fragmentation pattern gets us this fragment over here, which is a secondary carbocation again. So the 71 should be abundant because it gives us a secondary, and the 43 should be abundant because should gives us a secondary. Also, when we get the secondary cation, which is 43, we also could, by some small chance, get a primary cation from the other 43, the N-propyl fragment, which is also a 43. So that's why 43 is the most abundant here, and 71 is next. So that's very subtle. Same fragments, but different abundance. You can use the abundance as a clue to figure out what your structure is. You basically have to say, my structure explains this spectrum, or this spectrum can be used to defend my suggestion about what the structure might be. So let's try one. Let's start from scratch, just from the spectrum, and let's think like a detective, and as a chemist, of course. Now, the first thing that I like to look for are isotopic signatures, meaning, do we have nitrogen or sulfur or chlorine or bromine or iodine? And in this case, we don't. Remember, iodine, we would see a large gap separating our fragments by 127 molecular weight units. We certainly don't see that here, so there's no iodine. Bromine would have an M and M plus 2 pattern at 50% equal abundance. Chlorine would have an M and an M plus 2 pattern at 1/3 abundance. Sulfur would have it at 4% abundance. We don't see any of those patterns. And nitrogen would have an odd parent with even fragments. And in fact, here we have an even parent, 84, with odd fragments. You can see it's 55, 69, 43, and 29 and 27. So we don't have any isotopic signatures. So let's assume for now, let's ignore oxygen for a moment. Let's assume that we just have carbons and hydrogens. Now, what's our molecular weight? Remember that our molecular weight is the same thing as our parent ion. Our parent ion is the radical cation that has lost an electron but not fragmented. So our molecular weight is 84. Now, from that, since we know that we only have carbons and hydrogens, again, we'll talk about oxygen in a moment. Since we know we only have carbons and hydrogens, let's figure out what the formula must be to give us the molecular weight. Remember that carbons and hydrogens will always bind to each other at certain ratios. So here's what I do. I say, okay, if we had C6, 12, 24, 36, 48, 60, 72, that gets us close. 6 carbons gets us close. Then all we need to do is add 12 hydrogens to our formula to get 84. So that means C6H12. And you can calculate the index of unsaturation. There is one index of unsaturation for that, which means that there is a double bond or a ring on our structure. If you don't remember index of unsaturation, go back and look at the alkene chapter, and it talks about how you can figure out the existence of double bonds or triple bonds or rings by applying a formula to the ratios of carbons and hydrogens. C6H12 gets you an IOU of 1, which means that we've got one double bond or one ring. So now I look at our fragments, and I usually look for the common alkyl fragments to see whether they are there or whether they are there with some sort of modification. For example, we've got a 55. Now, 55 is close to 57. 57 is what we saw for butyl. So 55 is basically butyl minus 2 H's, which makes me think that there's a 4-carbon alkene. These are 2 possible fragments for a 4-carbon alkene. We can basically have 4 carbons in a row, 4 carbons in a chain, or we can have 3 carbons with a 1-carbon branch. That gives us 4 carbons in a fragment, and plus we know we've got the double bond there. That double bond removes 2 hydrogens from our structure and gives us a 55 instead of a 57. We've also got 43, which is our propyl fragment or isopropyl fragment. We've also got 29 and also a 27. So 29 was ethyl, and of course 27 is just our ethyl minus 2. We've also got a peak at 69 right here, which is 84 minus 15. So here's what I'm thinking is that 84 is our parent. Whatever 69 is our parent minus a methyl. So we need to have a fragmentation site on our parent that allows us to lose just the methyl group somewhere. We also are going to have some fragment with 4 carbons and a double bond for 55. We also need to have some fragmentation pattern that gives us a 43, either as a propyl or isopropyl, and another fragment that gives us 29 or 27, which would be ethyl. So here are some thoughts. Here's 6 carbons. 1, 2, 3, 4, 5, 6. We've got our double bond. That double bond gives us a molecular weight of 84. Now, this explains pretty much all of our fragments. We can explain our 69 peak. We can lose a methyl. If we lose a methyl from this site right here, we cleave right there, then we lose a methyl. We can get a 55. 55 we would get from this fragment right here, which is fragmenting right there, that cleavage site. So cleaving at that bond gives us a 69. Cleaving at that site gives us a 55. Cleaving at this site gives us a 43. Here's our 43. 1, 2, 3. So that's our propyl group. And we can also lose our ethyl. Cleaving at this site also gives us our ethyl. So actually cleaving at this site not only gives us our 55, it also gives us our 29. And cleaving here gives us our 43. Cleaving here gives us our 69. Now, what about here? All I did was I took, instead of a 6 carbon chain, I made it a 5 carbon chain and moved our methyl group over. So we now have a branch. Now, this gives us an isopropyl fragment. If we cleave right there, that gets us isopropyl, which is 43. We can also lose a methyl, which is 69. We can lose this methyl right here or this methyl right there. I guess we could lose this methyl over here as well, which we could do over here. But we have no way of getting an ethyl peak. There's no cleavage site here that would give us an ethyl. We don't cleave double bonds. I don't think I mentioned that. But double bonds are not easy to cleave. If you lose one electron, that electron is going to go out of the pi bond, and that's not going to end up cleaving the sigma bond as well. So typically these fragmentation sites are always sigma bonds. And we can't get an ethyl from here. In fact, I don't think we can get a 55 either. I think this is a mistake. I don't think we can get a 55 from this either. So this structure doesn't really work because it doesn't give us the fragmentation patterns that our spectrum showed us. Same thing over here. This gets us an ethyl. We can cleave right there to give us an ethyl, 2 carbons. We can cleave also that site over there, gives us our 55, this piece on the left, that's 55. We can also lose a methyl to give us our 69, lose that methyl there, or that methyl there, or this methyl here. But we can't get a propyl or isopropyl from this. Again, we can't cleave that double bond. So this molecule gives us no explanation for the 43. This molecule gives us no explanation for the 29 or the 55. But this pattern here explains all of the peaks that we saw. So I would guess that this is the structure corresponding to this spectrum. Okay, let's talk about other common fragmentation sites. Typically, what you want to look for is the heteroatom. By heteroatom, I mean some non-carbon hydrogen atom. So look for the heteroatom, then look for the adjacent carbon, and then cleave the bond. So heteroatom, carbon, cleave. The reason you cleave there is because you get the carbocation on the C that is resonance stabilized by donating a lone pair from the N. Here they've already done that. They've taken the lone pair off the N, made a double bond to the carbon to delocalize the charge off of the carbon onto the nitrogen and satisfy the octet rule for all of our atoms. So cleavage at this site is expected because the resulting cation is stable. So heteroatom, carbon, cleave. For ketones and aldehydes, it's the same thing. Heteroatom on the oxygen, carbon, cleave. Again, cleaving at that site gives you a carbocation that can receive a lone pair from the oxygen and get us the resonance stabilized charge. This has the positive charge delocalized off the carbon onto the oxygen, and all of our atoms still have an octet. So heteroatom, carbon, cleave. Here for ethers, heteroatom, carbon, cleave. Again, that carbocation can accept the lone pair from the oxygen, and you end up with the resonance stabilized cation. You can lose directly off of the heteroatom sometimes. So here we already saw heteroatom carbon cleave above, but this is just cleavage straight on the heteroatom. That's because the heteroatom will have a polarized bond, and that bond will be more likely to cleave. Often with this pattern, you get rearrangements. Notice that we've moved the hydrogen off of our carbon onto the oxygen. That gives us a carbocation, which is then resonance stabilized. So there's a cleavage and a rearrangement. Because the mass spectrometer involves forming lots of high energy fragments, carbocations and radicals and things like that, there are often lots of opportunities for rearrangement. So if a molecule has an atom that seems to have moved from one atom to the next, or some double bond moves inexplicably, that's often okay. That can be explained by having rearrangements occur in the flight path. Now let's talk about oxygen. In our previous slide, I showed you that oxygen can induce predictable fragmentation patterns. If it's on a ketone or an aldehyde, it will cleave adjacent to the carbon. If it's on an ether, it will cleave adjacent to its carbon, or perhaps directly on the oxygen. If you have alcohols, though, alcohols will often dehydrate in the spectrometer, meaning you will end up losing a fragment of 18 molecular weight units. Here's our alcohol with some even molecular weight. It's a radical cation. That will perhaps lose water. We lose the H and the OH. It's kind of like a dehydration reaction, an elimination reaction. We get the double bond and we lose water, which has 18. Notice that this is still considered the radical cation. This has not cleaved. We just underwent a reaction. So sometimes you will find that your parent or other fragments are 18 less than they should be, or 18 less than what might make sense. And you can explain that by suggesting that there was an alcohol on that fragment and it simply dehydrated in the machine. So look for dehydration. You can also, of course, look for that cleavage. Heteroatom, carbon, cleave. That again gives you the carbocation that can accept the lone pair from the oxygen, get you a resonance stabilized cation, and the other side will get the radical, which is of course not detected. So those are typical oxygen fragmentation patterns. Oxygen does not have any significant isotopic effects, so you won't see oxygen 17 or oxygen 15 or oxygen 18 in your spectra. So you have to look for other signs of oxygen. Here's an example of a dehydration pattern starting from 3-methylbutanol. That's this guy right here. So this is a butane with an alcohol. So it's a butane 1-ol, and then it's got a methyl on the 3. So 3-methyl butane 1-ol. This, let's assume, is our parent ion. It's lost an electron, but is not yet fragmented. It could lose water from the parent and get you a new parent, which is less molecular weight by 18. So this was 88. In fact, they're showing you here. They're saying you can't see it, but the parent peak is very tiny at 88. So there's 88. If we lose water, our new parent will be 70. And that is here. It's our parent minus 18. We could also lose water and fragment. Notice that when we lose water, we get a double bond, which makes fragmentation at this carbon, at the allylic carbon, very favorable. If we lose that methyl group as a methyl radical, then the cation will be on the other carbon, our allylic carbon. That is 55. It's resonance stabilized and should be our base peak, should be the most favorable fragmentation site. So here's our parent at 88. We can lose water to make 70. We can then lose another methyl to make 55. We also have a cluster around 43, which means that's a propyl. Notice that if we cleave right here, on this bond right here, we get a propyl. In fact, it's an isopropyl, which is secondary. So that should be a pretty good fragmentation site. And you see it is. It's just as good as 70. We also have a cluster around 29, which is an ethyl. So we need to explain how we lose an ethyl. Notice over here, once we lose the methyl to give us our allylic cation, we can lose an ethyl from this fragment right here. That would give us the ethenyl radical and the ethyl cation. So you get cleavages from cleavages and other rearrangements or eliminations to explain your pattern. It just has to be logical. It has to obey the chemistry as we know it. We can't just expect things to happen willy-nilly. We have to have a logical explanation for it. So one last practice exercise is I want you to account for the peaks at 87, 111, and 126 in the mass spectrum of 2,6-dimethyl-4-heptanol. That's this structure here. Look at this structure, see if you can figure out the peak at 126, the peak at 111, and the peak at 87. Explain what fragmentations must be happening to allow for these peaks to happen. Also, I'm going to throw in a bonus, see if you can figure out the peak at 69. I'll go over them in a moment. You can pause the video and work on it on your own, see if you can figure out all 4 of those, and then I'll give you the answer in a moment. Here are the answers to the practice problem, where I gave you 2,6-dimethyl-4-heptanol, and I wanted you to explain the formation of the peaks at 69, 87, 111, and 126. Now, hopefully where you started was to figure out what the parent ion was. Now, in the spectrum, there was no parent ion. There was no M+, because if you calculate the molecular weight of 2,6-dimethyl-4-heptanol, it weighs 144 molecular weight units, and the parent was 126. So we're missing some mass there. And if you think about it, 126 is 18 less than 144. So our 126 peak would come from our parent peak of 144, losing water. So what I've drawn here is the elimination product starting from our parent molecule. So that is our 126 peak. Now, 111 is 15 less than 126. So I'm thinking that we can explain the formation of a 111 fragment by losing a methyl group from our 126. The reason that I'm choosing that methyl group, or in fact, it could be this methyl group as well, they're equivalent. The reason I'm choosing one of those and not one of the other methyls is because the two methyls in green, losing those as methyl radicals would leave us with an allylic cation. That cation right there is in the allylic position. It's adjacent to that double bond, which means it's resonance stabilized. So 111 comes from loss of a methyl from our 126 structure to give us an allylic cation. We can explain 87 by following our cleavage pattern for alcohols. We can look at our structure and go, we've got a heteroatom and then a carbon, and then we're going to cleave. So that cleavage site, again following heteroatom, carbon, cleave, would give us those two potential cations. A 57 if it cleaved to give the cation on the left side, and an 87 if it cleaved to give a cation on the right side. Now, notice in our spectrum that 57 wasn't a major fragment, but 87 was. And that means that in this fragmentation site, it's always going to cleave to give the 87 cation and the 57 radical. Why would it do that? Again, the reason why it would ever cleave always in one direction is because that particular cation must be stabilized in some way. And in this case, as we know from our alcohol cleavage pattern, the cleavage at that site gives a resonance stabilized carbocation. We can take the electrons down off the carbon and bring them down to delocalize the carbocation. So that's our 87. The hard one, the tricky one that I threw in after the fact, was to explain 69. Explain how we can get a fragment at 69, which was a fairly significant peak on our spectrum. The way you can explain 69 is that it's loss of water from our 87. 69 is 87 minus 18. And our 87 fragment right here has our water on it, has our oxygen on it still. So if we lose water, we do some kind of dehydration. We're gonna take away one of the adjacent hydrogens right there, give us a double bond right there. Now, that means that our carbocation has to go somewhere else. So I'm just gonna say that our cation is somewhere, just put the whole molecule in brackets and say, this is charged somewhere, we're missing a hydrogen somewhere. That's clearly a rearrangement, but it shows up on the spectrum. There is a peak at 69. And the only explanation for that peak is if we lose water from our 87 fragment. That's it for lecture 4. For workshop, I'm going to have practice problems for you to do on the board.